Okay, we're going on to section 7.3, the scalar product of two vectors. The scalar product, also called a dot product, is A dot B is defined as AB cosine theta. Now that's the magnitude of A, the magnitude of B times the cosine of the angle between them. So we define work is F dot R. So we have the magnitude of the force times the magnitude of the displacement times the cosine of the angle between them. And now notice that in AB cosine theta, well, we have F dot R. You don't have to have the same units. F is in newtons, R is in meters, so you get Newton meters, and that's joules. So the A and the B, they don't have to have the same units. Now, let's go. We got a cat trying to enter the picture here. Let's look at a graphical view of the scalar product. If you look at A and you look at B, you'll see that B is the projection of the B cosine theta is the projection of B onto A. It's just basically the horizontal component of the B vector. So that gives you a visual understanding of what it is. A dot B is equal to AB cosine theta. It is commutative. A dot B equals B dot A. So it is commutative. It also obeys the distributive law. A dot B plus C is equal to A dot B plus A dot C. Now, if they're perpendicular, if A is perpendicular to B, since theta is equal to 90, AB, and the cosine of 90 is equal to 0, A dot B equals 0 when the two vectors are perpendicular. If the two vectors are parallel, then the angle between them is 0, and the cosine of 0 is equal to 1. So A dot B in that case is just equal to AB. And if they're parallel but in opposite directions, the cosine of 180 is -1, and so A dot B when they're in opposite directions is minus AB. Now, whenever the cosine is greater than 90 but less than 180, it's going to be negative, just because the cosine in the second quadrant is negative. So it's going to be a negative quantity. It's going to be AB cosine theta. But if you just put in the actual value, you should get the value that you're looking for. Now let's look at unit vectors. We see here A, J, and K. Those are unit vectors. They're orthogonal one to the other. So if we do the dot product, any dot product of a vector upon itself will equal 1. A dot J, stop that. Leave that alone. Sorry about that. There's a cat messing with stuff it shouldn't. I dot I equals J dot J equals K dot K equals 1. And also, if you look at the orthogonal, since the cosine of 90 degrees equals 0, A dot J equals, that should be A dot K, not I dot J repeated. So I dot J, I dot K, and J dot K all equal 0. So in the if we look at A, if A is AXI plus AYJ plus AZK, and B is equal to BXI plus BYJ plus BZK, if you dot those everywhere where you get, we would multiply each term by itself, but everywhere you have like a IJ, I dot J, or I dot K, or J dot K, those all equal to 0. And everywhere you have a I, J, J, and KK, such as AXI times BXI, or AXI dot BXI, you'll get a 1 between them. So the A dot B is equal to AX BX plus AY BY plus AZ BZ. You should be able to prove that to yourself if you do out the long multiplication um, using the distributive property that we saw earlier. And A dotted upon itself or B dotted upon itself will be AX squared plus AY squared plus AZ squared is equal to just A squared, the magnitude squared. Okay, I think that's it for that. Let's look at this. Which of the following statements is true about the relationship between the dot product of two vectors and the product of the magnitudes of the vectors? AB is larger than AB, A dot B is larger than A times B, A dot B is smaller than AB, A dot B could be larger or smaller than AB depending on the angle between the vectors, or AB could be equal to AB. And if we look, it could be true that A dot B could be equal to AB because the range of the values of theta, or in particular cosine theta, is from -1 to +1. So they could be equal. It's not necessarily smaller. It's not necessarily larger. They could go very well, but I don't think it'll ever be larger because cosine theta will never be greater than 1. But it could be equal. Okay? Now, here's another one. The vectors AB are given by A equal 2I plus 3J and B equal to -I plus 2J. Determine the scalar product of AB. Well, if we do it the long way, we have 2I plus 3J dotted with -I plus 2J. And if we use the distributive property, we first take that 2I and distribute it among the I and the 2J. We get 2I dot I plus 2I dot J. And then we take the plus 3J, the second half of the A vector, multiply it distributively to the -I plus 2J. We get -3JI plus 3J 2J. Well, the I dot J and the J dot I are both going to be 0, and the I dot I and the J dot J are both going to be 1. So we end up with 2 times 1 plus 4 times 0 minus 3 times 0 plus 6 times 1. So we're going to end up with a, well, they missed a minus at the beginning. -2 plus 6, and that's equal to 4. So this is strictly a mathematical exercise in the dot product. Okay. Now, if we just use the formula that we had previously, AX BX plus AY BY, it's much simpler. You get 2 times a -1 and 3 times 2. So a -2 plus 6 equals 4. That's the more direct approach. You don't have to go through the exercise of doing the I dot J and the J dot I because we already know that those terms are going to be 0. Okay, let's find the angle between A and B. Well, we can get the magnitude for A and the magnitude for B. And if A dot B is equal to cosine theta, if A dot B is equal to AB cosine theta, well, cosine theta is equal to A dot B divided by the magnitude AB. So you get 4 divided by square root of 13 times square root of 5. That's equivalent to the 4 divided by the square root of 65. So if you work that out, theta being the cosine, arc cosine of 4 over square root of 65, you get 60.3 degrees. Okay, let's look at work done by a constant force. We're going back one section, we're going to apply the dot product to a force and a distance. A particle moving in the xy plane undergoes a displacement given by r equal 2I plus 3j meters as a constant force of 5I plus 2j newtons acts on the particle. Calculate the work done by F on the particle. The work is equal to F dot R, so that's 5I plus 2j newtons times, or dotted with 2I plus 3j meters. And if we just do the 5 times 2I plus 2 times 3j, we'll get 10 plus 6. I don't know why they did it the long way when they just showed you that you can do it the short way. And you end up with 16 joules. And this completes our discussion of the scalar product. Next, we will discuss section 7.4, work done by a varying force.